So I designed today's talk mainly focused on that perspective, where I will talk more about some problems that we can address with the help of computational intelligence, data science, and cloud computing. So if I look at the this particular trend, this graph visually represents the growing interest in areas like data science, cloud computing, social good, computational intelligence over time. And this is actually sourced from Google Trends. And if you look at this graph, you can see that in the last decade, from the last decade or at the beginning of the last decade, there is a huge popularity of all these particular topics. And it clearly indicates a significant surge, particularly in data science and cloud computing. And during the end of the last decade, there is a huge thirst on the artificial intelligence data science field. So these technologies, mainly computational intelligence, shows a more gradual but sustained interest. And thus the convergence of all four is very crucial, as we will see in the next slides. So there is a very need for convergence in technology for social good. When I'm talking about social good, I'm actually trying to think about some problems which are present in our day-to-day life, or maybe in our surroundings. And those problems can be addressed with the help of different ICT, like information communication technology, right? So in the current scenario, there is a huge popularity of artificial intelligence, and with the artificial intelligence and the other technologies, it's quite uh, mm, interesting to address those problems. That's why it's about social good. Now, here you will see that some issues are highlighted, and they required uh, uh, attention, or they can be addressed by the convergent technological approach. These are very complex problems or the global challenges. As you can see, we are challenged with issues like climate change, unsafe infrastructure, environmental pollution, and public health crisis. So it seems like these are individual problems, but actually they are not. These problems are very interconnected, and they require solutions that are scalable, adaptable, and data driven. Isolated approaches are insufficient to address this. So therefore, there is a necessity for convergence. So when I'm talking about the convergence, I'm looking at it from that perspective. Now, here are three core pillars of our discussion. That is, computational intelligence at its heart focuses on enabling machines to learn and solve problems in a way that mimics human intelligence. And this encompasses artificial intelligence, machine learning, deep learning, computer vision, natural language processing, pattern recognition, and data science, which is concerned with the entire data life cycle, from collection and preprocessing to advanced analytics, predictive modeling, decision support, and spatiotemporal analysis. These are few things that I have highlighted here, but there are many subpoints also. Cloud computing provides the scalable infrastructure, because all of these problems have this potential of huge data generation, and they quite lead to the big data. And when we have this kind of environment where we have to tackle with the big data, infrastructure is a big issue. Cloud computing provides that infrastructural support. For example, the storage, computational power, real-time processing capabilities. Moreover, in the present scenario, most of these problems can be addressed with the help of sensors or IoT. So that IoT data integration is quite uh, easily managed with the help of cloud computing environment. AI models which are developed to address those problems can also be deployed in the cloud computing environment. So there is a necessary to support this computational intelligence and data science at scale. And it is the synergy of these three that allows us to sense, analyze, and act on real world problems quite effectively. So, what is our goal? Our main goal is to ensure that this deep technology serves humanity and contributes to a very sustainable future. So, in this particular slide, we try to highlight how the computational intelligence, data science, and cloud computing, this trio can be applied to achieve specific social good objectives. For instance, we can protect natural ecosystems using AI powered drone based plantation monitoring system. You know, this plantation, the forest department, they plant trees, and yearly wise they need to be monitored, whether the count of the trees and the different parameters regarding the trees. In the next slides we'll discuss about that. On the other hand, for smart agriculture, we can empower our farmers with intelligent tools like AI and IoT powered assistance systems, smart agriculture assistance systems. We can also make our cities smarter and safer through different type of systems. One could be like road anomaly detection system, because a good city is actually popular because of its fine roads. So maintaining the road condition of a city is a very important task. And if we have a very solid system where the road anomaly can be detected, then it would be very good for the citizen as well as the city authorities. So road anomaly detection systems that could leverage IoT, cloud, and AI. And we can also promote citizen health and well-being with solutions like, say, less polluted route. We may have a recommendation system where we will get less polluted route. So you can put a source to destination, and the system will recommend you some routes which are less polluted, and you can take one such route to travel. So these are just a few examples of the transformative potential. So now, for today's talk, I have considered four such case studies that my students, my research team are currently working on. And these are actually named as Plant AI, which is mainly the plantation monitoring, Road AI, which is actually about monitoring of the road condition, Air Sense, which is about air pollution monitoring, and Agri-Tech AI, which is about smart farming or smart agriculture. So these are very practical application of these technologies, or the convergence of these technologies. So let's briefly look at four case studies. So as I mentioned, that Plant AI that uses AI powered drones for plantation monitoring and a cloud-based repository for predictive analytics, enabling sustainable forest management and resource optimization. On the other hand, Road AI focuses on road safety by detecting road anomalies using AI and providing cloud-based geospatial mapping for citywide monitoring, leading to safer roads and efficient municipal maintenance. AirSense that employs IoT sensors and machine learning for pollution monitoring, providing AI-driven route recommendation like less polluted route and high granularity pollution maps to improve citizen health. And the last one is Agri-Tech AI, which uses an AI chatbot for regional language query resolution. And IoTs can be used for soil weather sensors for precision farming, and AI drones for targeted pesticide spraying. ultimately increasing crop yield and cost savings for farmers. Each of these case studies demonstrates the power of computational intelligence, data science, cloud computing, and moreover, the convergence in addressing specific social challenges that I discussed. So let's look at this first case study in a more detail. So this is about AI-powered drone-based plantation monitoring and management system. So basically, this an it simply exemplifies how advanced technology can address critical challenges in forest management. So Plant AI was conceived to tackle several key problems in traditional forest plantation management. As I mentioned earlier also that forest department can plant trees in a big area, and then year-wise they need to monitor that. And this include this difficulty in achieving this timely and accurate monitoring. Because there is this lack of proper tools for plant health and parameter assessment, resource shortages for effective monitoring, and the absence of digital repositories and predictive analysis capabilities, and the lack of decision support system. Usually, the traditional system is very manually handled by one or two person, and uh, they are supposed to wander in the forest and to count the number of trees or to check manually the health of the tree like this. So these limitations lead to inefficiencies and hinder effective forest management practices. So Plant AI offers a solution through the automation of plantation monitoring and leveraging AI-powered analysis of drone captured imagery and video. A core component of this is automated tree detection and species identification. For example, in this slide, you can see that there is a marking of two specific species, like species A and species B. So the system is trained to accurately identify the presence of trees within the imagery and classify them into different species, as you can see in the previous slide. Now, beyond mere detection of plant AI, also automates tree counting. So this is essentially for inventory management and assessing plantation density. As you can see, the system can provide precise counts. For example, a count equals to 43 directly from the drone imagery. This level of accuracy is often unachievable with manual methods, which is actually the traditional method of forest department. So Plant AI goes further by estimating key tree parameters. For example, tree height or girth measurement, average crown spread, or trunk circumference, and vertical height. So these parameters are crucial for assessing the tree health, growth rates, and overall plantation development. The the ability to derive this metrics automatically and accurately is a very significant advancement, and which is possible with the help of artificial intelligence and computer vision. So in this slide, I tried to explain the methodology. The methodology behind Plant AI relies on this advanced drone technology. These drones are actually equipped with very sophisticated sensors, including high resolution camera modules. Beside the camera, we also have LiDAR sensors, such as Velodyne LiDAR system. This combination of sensors allows for the capture of both high resolution imagery and precise 3D point cloud data. So for tree detection and species identification, Plant AI employs state-of-the-art predictive models, specifically the Yellow version 8 architecture. Yellow V8 is a highly efficient and accurate object detection model that enables the system to identify and locate trees within the drone imagery, as well as classify them. We can also use recent advanced yellow variants like yellow V11 or yellow V12. So we can change this model as there are many new models are coming up. So here what you can see that this image, so the first thing is that from the camera image we can detect the tree, we can also classify them, and as I mentioned that along with the camera we also have lidar sensor. So this involves a multi-stage process. So first we analyze the raw forest point clouds generated by the lidar sensor. This data is then segmented to isolate individual trees. Finally, from this segmented data, we extract key metrics such as tree top location, tree height, and the crown diameter. This 3D this 3D spatial information actually adds another layer of valuable data for comprehensive forest analysis. So next is uh, to illustrate this application of plant AI, we performed a case study in the Radhanagar forest range under Bakura North Division of West Bengal. This shows the specific study area, highlight the geographical coordinates of the region. And then you can see some of the snapshot of field data collection here. So next time, look, I'm explaining that the case study in different parts, starting from the data collection, predictive data modeling, and inferencing. These are actually the three main steps. So data collection involves aerial image capture followed by annotation of sample data. All data are then stored in a cloud repository for remote access and historical analysis. This data are then used for predictive data modeling. As I mentioned earlier that we have used yellow version 8 model for tree detection and species identification and the associated confidence scores. We perform predictive modeling and interferencing for first year and third year plantations. We have faced many challenges also, and if there are some challenges, it's good to continue your research because that gives you some problems and you can dig on those problems to figure out a much better uh, solution. So this shows the real world data collection using drone. Now here you can see that data annotation phase. We have used RoboFlow for data annotation. This process involves labeling the trees in the images. And once trained, the model can perform real-time prediction or on video or static images. So this is actually that video captured by the drone, and then when we have integrated the AI model along with it, so it can show the the tree, the species, and the confidence of identification. So once it is trained, the model can perform real-time prediction on video and static images, as you can see here. These here this bounding boxes and the confidence scores are shown in this diagram. So this is for the first year and third year plantation. And here you can find some of the performance results like the epoch summary of the model's training process, which includes key metrics such as GPU memory usage or box loss, classification loss, various precision and recall measures. These metrics are actually essential for evaluating the model's performance and ensuring its accuracy. Here you can see the training and validation loss curves for the model. These graphs illustrate the model's learning process and help identify potential overfitting or underfitting issues. Additionally, we have metrics on precision and recall, which demonstrate the model's effectiveness. So plant AI's capabilities extend beyond basic forest and plantation monitoring. It has a range of use cases, including industrial decarbonization, reforestation, and afforestation efforts, timber yield prediction, biodiversity conservation, wildlife habitat assessment, and many more. So this is a very beginning of this kind of research. It has highlighted the versatility and potential impact of plant AI. So we have many future plans to extend this work and to cover the other use cases also. So next I will move to the next case study, which is the road AI. Or road eye, in short, you can say. Road eye mainly about road anomaly detection and mapping system. So it brings together IoT, artificial intelligence, and cloud computing to uh, to build a system that can monitor the road condition uh, in our locality. So the condition of our road infrastructure is quite a major concern in both urban and rural areas. And the key challenges we identified are like uh, accurate detection of the anomalies like potholes, cracks, and uneven surfaces. Then we need a monitoring system that maintain up-to-date knowledge of road conditions across entire city networks. And finally, we need mapping where we can visualize anomalies on geospatial maps so that the authorities can act effectively and prioritize their maintenance. So current systems are either manual or too expensive to scale. Road AI tries to address this gap. So we have published some papers in this topic also. If you are interested, you can dig more on this. So next, I will try to show you the overall flow of the system, which is based on IoT cloud-based architecture with integrated AI analytics. So how it works. Now, suppose we have a road network. Image and video data are collected via a smartphone-based system mounted on vehicles or autonomous drones, or any citizen can also participate in this venture, which is termed as participatory sensing. They can also take the picture of the road condition and can be used in the system. So next is this, we need to annotate that data. We can employ deep learning object detection models like yellow and mask RCNN to identify the road anomaly. So basically it's a object detection model. Different models perform differently and they have their own merits and demerits. After that, data is streamed and processed in real time using cloud infrastructure, because that is very important here. Real time response is also very important. And finally, we will have a web-based dashboard which visualizes road conditions and highlights anomaly-prone zones and even suggest after safer alternative routes. Similar to this plant AI, this ELO-based models are utilized for the core task of anomaly detection. These models are trained to analyze the image data and identify the specific types of road anomalies. The output of the model is then used to generate road anomaly maps, and these maps visually represent the location and type of each detected anomaly, enabling efficient planning of maintenance and repair operations. We tried many case studies for road AI, and for different type of field testing, many volunteers involved in this. We have captured many images and videos also. So some example here you can see the phone is actually mounted in the scooty, and then when he took the ride, then that collected images and In that image, the road anomalies are marked. So this work is a very interesting work, and the development of road AI relies on a combination of different type of tools and technologies. It's not only any specific one technology. It is not like that. We have used many technologies like for data annotation, RoboFlow, which streamlines the labeling process. For model building, we have used YOLO, implemented using libraries like Ultralytics. This actually highlights some of the code snippets demonstrating the use of Ultralytics and RoboFlow for model training and dataset management. So next, let's move to the third case study, which addresses a rising concern in both urban and semi-urban environments, that is air pollution exposure. So we have developed a system called AirSense, a very high-resolution pollution sensing and route recommendation platform, again, which is based on IoT, AI, and cloud infrastructure. AirSense empowers citizens to make a healthier decisions about where and when to travel and whether it's a daily commute or recreational walk. It can also aims to answer very relevant questions like, can we help people choose routes that minimize their exposure to polluted air? So to achieve this, we developed a system that enables high granular spatially continuous pollution mapping, and uses it to recommend less polluted paths in real time. So in this slide, you can see that dashboard, the main device, IoT device, the high granular spatial continuous pollution mapping, and a screenshot of less air polluted route, along with a, a snippet of the whole thing. So we have also filed a patent on this. Let's see what happened with that. So this is a very interesting work, and it also has a huge potential. So now let me dig some more in the technical part. Where you in this slide you can see that it is using multi-view data fusion technique to achieve accurate spatiotemporal pollution mapping. So basically, in air sense, this spatiotemporal pollution mapping and high granular mapping is very important. So here it integrates both spatial and temporal views of pollution data. Uh, One algorithm is shown in this slide. The process involves predicting pollution levels at points of interest by considering data from different type of sensors. Okay, because different citizens at different time can contribute that data. So different various sensors are there, and over time it is collected. So the main purpose of this algorithm is to assign some weight over that, and finally it uses weighted averages to interpolate pollution levels and accounting for both spatial proximity and temporal relevance. So this fusion approach allows AirSense to generate continuous pollution maps even in areas with sparse sensor coverage, providing a more comprehensive understanding of air quality dynamics. So here you can see that there are two distinct views. One is the spatial view and another one is the temporal view. Spatial view of a dataset shows how pollution levels are distributed over the space. And on the other hand, temporal view of a dataset describes temporal variability of pollution levels at a particular point of interest. For each of these views, we used IDW interpolation for predicting pollution levels. So, in a case study conducted in the Jadavpur area of Kolkata, Airsense demonstrated its capabilities in a real world setting, and this system utilized participatory sensing based data collection. Uh, we have used our device called AQMD, air quality monitoring device, and the data underwent calibration, map matching, context aware data cleaning to ensure accuracy. The output included high resolution air pollution maps, as you can see in this slide, alongside the noise pollution, we have also we have performed two case studies, one on air pollution, another one is noise pollution. And these maps provide valuable insights into the spatial distribution of pollution within the case study area mainly. And as I mentioned earlier, that one of the key features of AirSense is its ability to provide less polluted route recommendation. In this case study, we considered three routes within the Jadavpur University campus. Those who know University campus, they know that we have 5 gates, and we considered three routes between gate number 1 and gate number 4 of GU for the case study. So this the first route goes completely outside of the university. The second one goes in front of the impact building and take building, and the third one goes in front of the Jhilpar and the guest house. So here you can see that the air and noise pollution levels along three paths, these three paths, and the rightmost route is found to be less polluted, and which is quite expected because the leftmost route is highly polluted to the others, because that is close to that is actually the main route, um, SC Malik route. So this is quite interesting. And now let's move to the last case study, that is AI and IoT powered smart agriculture assistance and precision spraying. Basically, the agriculture remains the backbone of our economy, but millions of farmers face serious challenges every day because they don't have direct access to this kind of technologies and resources. So problems faced by the farmers is mainly the lack of access to expert advice, unpredictable weather and soil condition, and moreover, there is no continuous monitoring of the soil condition and the local weather, overuse or misuse of pesticides and fertilizers, and sometimes that is quite bad for the crop as well as for the health of the farmers. Farmers may face different type of skin diseases and all those things. So for that, these problems they are facing because of this limited access to expert advice, and sometimes there is also the language issues because they used to speak in the local language, and the experts may use some other language, they proficient in English or maybe some other language, and this language issue is also there. And another issue is that relying on misinformation, sometimes they don't understand which is the right information, which one to follow and which one to not follow. So unpredictable weather and soil conditions, these things can be managed, or that can be addressed with the help of IoT.
Overuse or misuse of fertilizers and pesticides is very common, as farmers often rely on guesswork or incomplete knowledge. To address these problems, we need a smart farming system. We have developed an AI-powered system that listens to farmers' queries in their native language and processes them intelligently. Here's how it works.
So usually the farmer query analysis and AI-driven recommendations are follow this type of steps that I have mentioned in this slide. That farmers can make their query in local language. Then we'll have automatic speech recognition system that will convert from voice to text conversion, and that will be translated to standard English. So this will pass through a large language model for expert analysis and recommendation, and this will be used for example, they can make different type of prompts there, and that will be they can make their queries there, that will be translated to some specific language, and then that from that it will be converted to from voice to the text, and or text to the voice, and will feedback to the farmers. So this type of system is very important and will be very useful for the farmers, where they can make their query, they can get recommendations. So for IoT-based soil and weather monitoring, there are different issues like soil moisture, salinity, nitrate, potassium, phosphorus, oxygen, light intensity. These are different factors that pH value. These are different factors that set the standard of the soil for a good crop. And IoT devices can be very useful to continuously monitor these different levels. So here you can see the basic idea of the architecture. From different IoT devices, we can take these values, and that this continuous data can be stored in the cloud environment, where we will run our models to analyze those data, and we can get the inference out of that. So here we have used this AWS IoT and AWS Lambda, DynamoDB for data storage, Lambda for function programming, and S3 for storage. So the AWS cloud services are very useful to handle this kind of data. That also very there are different services also available through which we can build visualizations, and we can generate maps or reports that would be very essential for the continuous monitoring and analysis of the system. And there is one very interesting problem in this application is spraying pesticides. So basically the idea is the drone captured image. We will run an AI model in the drone, and by analyzing the drone captured event, we will identify the crop type. And based on the crop type, it is supposed to spray a specific pesticide. In this particular slide, you can see that from the color of this crop field, we can say that these are different type of crops, right? So say the pesticide 1 can be sprayed for crop type 1, and pesticide some other pesticides, say pesticide 2 for crop type 2. So this the identification of the crop type is first thing, and after that identification, the spraying of the pesticide. So two type of research challenges are there. One is identification of crop type, and another one is the spraying the pesticide. So we are looking at the three aspect of this whole system. One is building the autonomous drone. A second, building AI model for real-time crop type analysis. And the third problem is selective pesticide spraying. So here, this is also very interesting problem, where you can see that how nicely we can integrate IoT, drone imagery, drone based sensor. We can deploy intelligence in the drone so that it can spray pesticide according to the crop type. So this whole system is not is possible because of the convergence of this computational intelligence, data science, cloud computing, right? So here you can see some of our students, they have demonstrated they have built drone, and they have demonstrated that in ISTEC 2024. So one testing we have performed autonomous drone testing in the Jadavpur University campus. And so building drone and deploying intelligence in that drone is the current thing that we are working really very hard in that. And this one is a drone image of field survey in Bethuadhari in West Bengal. So in this image, you can also see that different types of crops, and that are very, I mean, just looking at the plain eye, you can easily say that the different type of crops are there. So these are currently my research team is working in this applications, and I just tried to show that how we are combining this different technologies to address different type of real world applications. I just want to stop here. Before that, I just owe a big thank to my research team. And I also want to share one news with you all, that our research team has currently formed a startup under Institution Innovation Council, IIC of Jadavpur University, which is named as GeoSense. And GeoSense is also the name of our research team, and we have published one paper on GeoSense. The Geo can be like Jadavpur University, and it can also be like judicious urban sensing. Because if you look at our works, you will see that most of our work is about judicious urban sensing. So that is a key thing of our research work. So that's why it is called GeoSense. So if you are interested in our work, please go visit our YouTube channel and just drop a mail to us if you have any query. We also have a website of the research team called GeoSense. So that is the information that I'd like to share with you. Thank you so much. So that's all from my side.